Today we're looking at domain and range and how they relate to functions. We're going to describe the domain and range of a function and also find the input-output pairs for a function. So let's look at this. The set of all inputs for a function is known as the domain of the function, and the set of all outputs for a function is known as the range. And if you look over to the left, the domain and range of a function can be written using set notation. For example, for the function that includes this set, 1, 2, 3, 4, and 5, 6, the domain is 1, 3, and 5, and the range is 2, 4, and 6. To help you remember this, we usually say that the first number is the x coordinate when we're graphing, and the second number is the y coordinate, if you remember from graphing. And so when we say domain, we usually mean the x range on a graph. Domain, and then the range would be the y axis of the graph. And so that might help you remember a little bit domain and range. Domain is your x coordinates going left and right, horizontal on the graph. Range is the y coordinates going up and down. So let's look at number 1. Consider a vending machine where inserting 25 cents dispenses 1 pencil, inserting 50 cents dispenses 2 pencils, and so forth, up to and including all 10 pencils in the vending machine. Identify the domain in this situation. Well, remember, domain is the input. Okay, so what we put in is how much money we get. So the domain is the money being inserted. So for this problem, the money that's being inserted is going to be 0.25, and then 0.50, and then 0.75, $1, 1.25, 1.50, 1.75, $2, 2.25, and then 2.50. Make sure that's 10 of them. We're going up to 10 pencils. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. Okay, number 2, we're going to identify the range, which is the pencils you get. So let's see if we can put it in the curly brackets, which we probably should have used the first problem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can get up to 10 pencils for the money that I put in. Number 2, for each function below, identify the domain and the range. All right, remember, domain is input, range is output. That's our definitions. So the input is going to be 7, 3, and 5. That's your domain. So let's put that in our brackets to show that we're including this set of numbers, 7, 3, 5. And then we'll click that and get the end of the bracket. The range, the output, is going to be 6, -2, and 1. So let me see if I can copy and paste this, if this thing would click when I want it to. What did we say? 6, -2, and 1. I'm just putting it in our brackets to show that it's a set of numbers. 6, -2, and 1 are the set of numbers that go along with the output, the range. Part B, similarly, you have the domain, which is the input, 2, 6, 8, and the range is what you get out, 4 and -3. Okay, domain 2, 6, 8, output range 4 and -3. You only get 2 things out, even though you put in 3 things, because 2 of the ones you put in give you the same output. Both 2 and 6 give you 4. So domain 2, 6, 8, range 4 and -3. Over on this graph, as I said in the beginning, the x will be your domain axis and your range will be your y-axis. And so the domain is going to be 2, 3, and 5. We can put that down real quick. 2, 3, and 5 will be the domain, the input, and then the range will be the y-axis, the output, 4, 1, and 3. Four, 1, and 3. Remember, curly brackets to show that it's a set of numbers. 4, 1, and 3 are your range. Part D, the domain is going to be, as I said, the x coordinate, -7, 9, and -6. The range is going to be your y coordinate, 0, -3, and 2.5. Domain, -7, 9, and -6. Range, 0, -3, and 2.5. Question 3. Consider a machine that exchanges quarters for dollar bills. Inserting $1 bill returns 4 quarters, and you may insert up to 5 $1 bills at a time. Is 7 a possible input for the relation this change machine represents? Justify your response. No, because you can only go up to 5. Put in 5 at a time. $5 bills at a time. Okay, 7 is not possible. It even tells you may insert up to 5, one at a time. So I can't put in 7. I can only put in 5, up to 5. So I can put in 1, 2, 3, 4, and 5. Could 3.5 be included in the domain of this relation? Explain why or why not. Well, you're inserting $1 bills, so you can't do $3.50. You can only go on the dollar ranges, $1, $2, $3, $4, and $5. So you can't put 3.5 into the domain. It's not going to be in there. In part C, what values are not in the domain and justify your reasoning? Well, as we just said, we can only put whole dollars in. So I can put no dollars in, 0. I can put $1, $2, 3, 4, and 5. 0, 1, 2, 3, 4, 5. So anything that's not any of those numbers are the values that are not in the domain. So 1.2, that's not in the domain. It has to be either 0, 1, 2, 3, 4, or 5. That's how many dollar bills you can put in. Anything else is not in the domain. D, is 8 a possible output for the relation that this change machine represents? Well, let's go back up to it. What do we get out? We get out quarters. Okay, we get out quarters. So we're going to get out 25 cents, 50, no, we're going to get out 4 quarters, 8 quarters, 12 quarters for 3, 15, no, 16 quarters, I'm sorry, for 4, and 20 quarters for 5. So is 8 a possible output? I mean, you will get out 8 quarters if you put in $2. So is 8 a possible output? Yes, it is. You'll get 8 quarters out if you put in $2. E, could 3 be included in the range of this relation? So will you get out 3 quarters? No. You put in $1, you get 4. You put in 2, you get 8. 3, 12. 4, 16. 5, 20. 0 and 0. But 3 is not in that range, okay? It's not included in this set that we're looking at. $1 will give you 4 quarters, okay? 3 is not in it. You can't put in $1 that would give you 3 quarters out. So what values are not in the range? Any of the numbers that are not 0, 4, 8, 12, 16, and 20. If it's not those numbers, you're not getting it out. Number 4, each of the functions that you've seen has a finite, means limited. If you remember the word we've used before is infinite, that means unlimited. Well, finite means limited. Okay, it's only a certain amount of numbers of ordered pairs. There are functions that have an infinite number, well, we just said it's unlimited, of ordered pairs. Describe any difficulties that may exist trying to represent a function with an infinite number of ordered pairs using the 4 representations of functions that have been described thus far. Okay, so why do you think it's harder to represent infinite numbers of ordered pairs than finite numbers? Well, just think about it. Could you write down infinite numbers of ordered pairs? No. Okay, when we did our set notation, we put them in the curly brackets. Could we write down infinite numbers? No. Okay, when we drew our map diagram, where we mapped one set of numbers to the numbers that they put out, could we map infinite numbers? No. No matter how we do, we're not able to write an infinite number of ordered pairs. That would be number 4. 5. Sometimes machine diagrams are used to represent functions. In the function machine below, the inputs are labeled X and the outputs are labeled Y. Domain and range. The function is represented by the expression 2x plus 5. So part A, what is the output if the input is 7, or if it's -2, or if it's 1/2? All right, let's look at this one. So a function machine, just a picture that looks like a machine, just to help you visualize what's happening. We're going to put in the X number and we're going to get out the Y number. Okay, we're going to put in the domain into this expression and get out the range. So if I put in 7, well then, just like we've done before, we'll replace the X with 7 and we will get 14 plus 5, which is 19. So input of 7, output of 19. How about when it's -2? Well, 2 times -2 is -4, plus 5 will give us 1. 2 times 1/2 is 1, plus 5 is 6. So there we go. We put in each one of them into the function machine and we got out the answers. The input, output. X is the input, domain, output Y, range. Is there any limit to the number of input values that can be used with this expression and explain? Well, let's look at the expression 2x plus 5. Is there any number that I could put in that wouldn't give me an output? No, it's fine. There's no limit on this. Let's look at this one. Consider the function machine below. This time we have a equation that has the exponents in it. So let's notice that one. Hopefully we all remember how to work with exponents. Use the diagram to find the input and output for the following ordered pairs. It's the same process though. We're going to replace the x's with these numbers and we're going to get out the answers. We'll do one of these. We'll do A. And so it's going to be -5 raised to the second power plus 2 times -5 plus 3. Well, -5 squared is 25 plus 2 times -5 is -10. 25 plus -10 is 15. 15 plus 3 is 18. That's all there is to it on these functions machines. Input, see what we get out. Make a function machine for this expression, 10 minus 5x. Use it to find the ordered pairs for 3, -6, 0.25, and 3/4. Let's just do one of them just to show you what we're talking about. We're going to replace the x with these numbers, and we're going to get out an answer, and then we're going to write it as an ordered pair, what we put in and what we got out. So if it's going to be 10 minus 5 times, let's say 3, well, that's going to give me 10 minus 15 is -5. And so my ordered pair is going to be 3, and the number I got out, -5. I put in 3, I got out -5. That's the ordered pair for this function machine that we would have made for this one. Okay? We put in 3, we get out -5. Creating a function machine can be time consuming and awkward. Yes, I did not draw the whole picture of the thing. The function represented by the diagram in item 5 can be written algebraically as the equation y equals 2x plus 5. Yes, that makes sense. For each function, find ordered pairs for -2, 5, 2/3, and 0.75. Create a table of values. Okay, so we're going to need a table. Let's see, we're going to have 1, 2, 3, 4. So let's make 5 rows because we want to label the first one. There we go, 5, and how many? We want 2 columns, input and output. Input, output. We'll put in -2, 5, 2/3, and 0.75. And let's see what we get when we do this. All right. 4 times -2 is -8. 9 plus -8 is 1. 4 times 5 is 20. Plus 9 is 29. 4 times 2/3, well, that's 8/3. Okay, which is 2 2/3. Plus 9, well, 2 2/3 plus 9 is 11 2/3. And then 0.75 times 4, well, that'll be $3, 3.00. Because, 75 cents and 75 cents is $1.50. And you do that another 2 times, so that'll be 4 times. So $3. 9 plus $3 is 12. There we go. That would be our input-output table for this equation. All right, check our understanding. This set of numbers represents a function. Identify the domain and the range of this function. Domain is the x coordinates 3, -1, 2, and 0. Those are the domain. 3, -1, 2, and 0. The range of the function will be the y-coordinates. 5, 2, 2, and -1. Just to remind everybody, the domain is going to be 3, -1, 2, and 0. The range, I'm going to copy and paste this, but I'm just going to change the numbers and and do stuff fancy, and then it backfires on me. The range is going to be 5, 2, 2, and well, we've already got 2, so we don't need to write it twice, and -1. Okay, domain and range. 10, identify the domain and range for each function. All right, the domain x coordinates -1, 0, 1, and 2. The range y coordinates 2, 0, -1, and -2. Domain 12, 17, -4. Range -8, 3, 9. Remember, input domain, output range. X coordinates domain, y coordinates range. Try 11 through 15 to see if you have any questions about this lesson.